Hello, and welcome to the TI Precision Lab module that discusses how to measure multiple RTDs, as well as the concept of conversion latency. The analysis presented in this series so far has focused exclusively on systems that only need to measure one RTD. However, many real-world applications require measurement of multiple RTDs. Moreover, most systems use a high-performance multiplexed ADC to minimize cost, size, and power consumption. Measuring multiple RTDs with a multiplexed ADC introduces many new design challenges that affect the system architecture and conversion latency. To begin the discussion, let's differentiate between the two types of multi-RTD measurement systems. Shown here are examples of the two types of multi-RTD measurement systems. On the left is an example of a system that measures multiple RTDs with the same wiring configuration, while the system on the right can measure multiple RTDs with different wiring configurations. Before we discuss the benefits and challenges of these different systems, let's clarify that wiring configuration refers to the number of RTD wires and has nothing to do with the composition. For example, the image on the left shows a system measuring two 2-wire RTDs. It is possible to measure a combination of platinum, nickel, and copper RTDs with this configuration as long as all RTDs only have 2 leads. Designing a system that requires the same wiring configuration for all RTDs is simple to implement and generally requires fewer ADC channels compared to the system on the right. However, the most obvious challenge with this system is that it can only measure one RTD wiring configuration. If the user needs to measure 2, 3, and 4-wire RTDs, they will need to design 3 separate systems. This Precision Labs module will analyze this system in more detail. Comparatively, the system on the right can measure a combination of RTD wiring configurations. The image shows a 2-wire RTD connected to the top terminal and a 3-wire RTD connected to the bottom terminal. This flexibility comes at the cost of more ADC channels per RTD. Moreover, some systems can require external jumpers to route the IDAC current to the correct channel. Systems that can measure different RTD wiring configurations are discussed in a subsequent Precision Labs module. Let's analyze the system on the left more closely. The system on the left, which uses a low side reference resistor, has the following design requirements. First, a maximum of 2 analog inputs are needed to measure each RTD. This specific implementation uses 8 analog inputs to measure 4 2-wire RTDs. Certain configurations are able to use fewer inputs. This is discussed in more detail on a later slide. Next, one IDAC output is required to bias each RTD. As shown, this system needs 4 separate bias pins, one of which connects to each RTD. Note that only one RTD should be biased at a time. The system also requires one differential reference input pair that is shared by all of the RTDs. This enables a ratiometric reference configuration. Finally, this system has a common return current path through RREF. This common current path is what enables all RTDs to share a single differential reference input pair, thereby minimizing the required external components. However, this common return path is also the reason why the IDAC can only bias one RTD at a time, even if the ADC or system supports multiple IDACs. This same system can be used to measure 4-wire RTDs as well, though this requires a different number of terminal connections. However, a more complicated design is required when measuring 3-wire RTDs or using a high-side RREF. Both of these configurations are discussed later in this presentation. Next, let's delve deeper in the process used to measure the multi-RTD system shown here. This slide steps through the measurement process for each RTD, beginning with RTD1. As shown, the IDAC current, highlighted in red, flows through RTD1, then through RREF and to ground. In terms of process steps, this requires the user to switch the ADC IDAC output to bias 0, then switch the analog multiplexer to measure between AN0 and AN1. The ADC then measures VN1, which is highlighted in blue. For RTD2, the IDAC current highlighted in green flows through RTD2, then through RF, and to ground. In terms of process steps, this requires the user to switch the ADC IDAC output to bias 1, then switch the analog multiplexer to measure between AN2 and AN3. The ADC then measures VN2, which is highlighted in blue. Before moving on to the next process step, it is important to consider analog settling issues due to the IDAC switching. Every time the IDAC output is switched, a previously unpowered circuit is biased, such that any capacitors in the IDAC path take some time to charge to a steady state. Avoid analog settling issues by switching the IDAC output as soon as possible after the previous measurement is complete. Switching the IDAC as soon as possible provides more time for any analog circuits to settle before the ADC begins converting the input signal. Now, let's move on to RTD3. As shown, the IDAC current, highlighted in orange, flows through RTD3, then through RF, and to ground. In terms of process steps, this requires the user to switch the ADC IDAC output to bias 2, then switch the analog multiplexer to measure between AN4 and AN5. The ADC then measures VN3, which is highlighted in blue. Finally, RTD4 is biased by the IDAC current highlighted in purple, which then flows through RF and to ground. In terms of process steps, this requires the user to switch the ADC IDAC output to bias 3, then switch the analog multiplexer to measure between AN6 and AN7. The ADC then measures VN4, which is highlighted in blue. This process can be repeated as many times as needed to continue taking multiplexed measurements. Before moving on to the next design architecture, let's revisit a comment made on the previous slide about reducing the number of required analog inputs. As discussed previously, the system shown on the left uses 2 analog inputs per RTD. This means each RTD is measured by one independent differential pair. For example, RTD1 is measured between AN0 and AN1. One benefit of this configuration is that it tends to make the PCB routing more symmetric and simpler. Though not shown, each RTD input requires an anti-aliasing filter comprised of resistors and capacitors. Choosing an independent differential pair for each RTD makes the placement and routing of these components much easier compared to choosing a solution with shared inputs. Additionally, independent differential pairs enable the component to be placed closer to the ADC pins. However, it is also possible to design this system using a single analog input per RTD, with another common analog input shared by all RTDs. This system is shown on the right. Using a common input is beneficial because it can reduce the number of analog inputs required by the system, thus allowing a lower channel count ADC to be used or enabling more RTDs to be measured. Note that in either case, the number of IDACs required per RTD is the same. As shown, AN4 is used as the common input for all RTDs in the system on the right. Using this configuration, RTD1 is now measured between AN0 and AN4. Further reductions in the number of required channels may be possible. For example, some ADCs have analog inputs that can simultaneously be used as reference inputs. This would combine the REF-P and AN4 pins in the system shown on the right. However, the main challenge with using shared inputs is that it can make the routing and placement of the analog filtering more challenging. Also, shared inputs are only possible where one of the analog input channels is connected to the common current return path. This is true for the 2-wire RTD system shown here, as well as a 3-wire RTD measurement system using one IDAC. On the other hand, it is not possible to reduce the number of analog inputs for a 3-wire RTD measurement system using 2 IDACs or 4-wire RTD configurations. Therefore, the rest of this presentation will use a system similar to the one shown on the left because it is generally applicable to all RTD configurations. Next, let's review some of the other possible multi-RTD measurement systems that use the same wiring configuration. Shown here is a system measuring multiple 3-wire RTDs using one IDAC. This system, which uses a low-side reference resistor, has the following design requirements. First, a maximum of 3 analog inputs are needed to measure each RTD. This is because 2 measurements are required to determine the RTD output voltage in this configuration. Refer to the Precision Labs module on challenges with 3-wire RTD systems for more information. Next, one IDAC output is required to bias each RTD. As shown, this system needs 2 separate bias pins, one of which connects to each RTD. Note that only one RTD should be biased at a time. The system also requires one differential reference input pair that is shared by all of the RTDs. This enables a ratiometric reference configuration. Finally, this system has a common return current path through RREF. This common current path is what enables all RTDs to share a single differential reference input pair, thereby minimizing the required external components. However, this common return path is also the reason why the IDAC can only bias one RTD at a time, even if the ADC or system supports multiple IDACs. The main benefits of this system are that it requires fewer IDAC outputs compared to a 3-wire 2 IDAC system, and it is not necessary to consider IDAC mismatch error. The main challenge with this system is that it requires 2 measurements per RTD to generate the final result, doubling the measurement time compared to a 3-wire 2 IDAC system. Shown here is a system measuring multiple 3-wire RTDs using 2 IDACs. This system, which uses a low-side reference resistor, has the following design requirements. First, 2 analog inputs are needed to measure each RTD. In this specific configuration, it is not possible to combine analog inputs because the RTD is biased by 2 IDACs. Next, 2 IDAC outputs are required to bias each RTD. One IDAC connects to the upper lead, while the second IDAC connects to the middle lead of each RTD, and both IDACs need to be enabled at the same time. However, only one RTD should be biased at a time. Refer to the Precision Labs module on challenges with 3-wire RTD systems for more information. The system also requires one differential reference input pair that is shared by all of the RTDs. This enables a ratiometric reference configuration. Finally, this system has a common return current path through RREF. This common current path is what enables all RTDs to share a single differential reference input pair, thereby minimizing the required external components. However, this common return path is also the reason why the IDAC can only bias one RTD at a time, even if the ADC or system supports multiple IDACs. The main benefit of this system is that it only requires one measurement per RTD, reducing the measurement time compared to a 3-wire RTD system using one IDAC. The main challenge with this system is that it requires 2 IDAC outputs per RTD, and therefore requires more ADC pins compared to a 3-wire RTD system using one IDAC. 2 IDACs also require consideration of IDAC mismatch error. Now, let's consider how the analysis changes if a high-side RREF is used. Shown here is a system measuring multiple 2-wire RTDs, similar to the one introduced at the beginning of this presentation. Unlike the previous configurations, however, this system uses a high-side RREF, resulting in a different set of design requirements. First, a maximum of 2 analog inputs are needed to measure each RTD. This specific implementation uses 8 analog inputs to measure 4 2-wire RTDs. Reducing the number of analog input channels is possible for a system using a high-side RREF. However, any reduction in the number of analog inputs is subject to the same benefits and challenges that were previously introduced for a system using a low-side RREF. Please refer to that slide for more information. Next, only one common IDAC output is required to bias all RTDs, because the IDAC current must first flow through the high-side RF. In this configuration, it is only possible to bias one RTD at a time as required. The high-side RF requires one differential reference input pair that is shared by all of the RTDs. This enables a ratiometric reference configuration. After the single IDAC flows through RF, it must be distributed to each RTD in the system, requiring an external multiplexer. Finally, this system has a common return current path to ground. As shown, a bias resistor might be required to level shift the RTD output signal into the common mode range of the ADC. However, this is not always required, and the bias resistor does not need to be a precision component. One of the benefits of using a high-side RF is that fewer IDAC outputs are required. Also, some ADCs include GPIO pins that can be used to control the external multiplexer. This can help reduce the number of isolation channels required in an isolated RTD measurement system. The most significant challenge with this solution is that it requires at least one external component to route the IDAC current, which in this case is a multiplexer. Additional multi-RTD configurations using a high-side RF are not discussed in this presentation. Instead, turn any of the previously discussed configurations using a low-side RF into a high-side RF system by applying the single IDAC plus single RF plus external multiplexer circuit shown here. That concludes the analysis of multi-RTD measurement systems that use the same wiring configuration. Let's now consider how using a multiplexed ADC to measure multiple RTDs impacts the system measurement time. Shown on the left is a two-channel RTD measurement system designed for two-wire RTDs. We have analyzed the architecture and operation of this circuit in great detail throughout this presentation. However, another important consideration for this system is how the ADC conversion latency affects the overall timing. The image on the right defines conversion latency as the time from the start of conversion to the time when data is ready to be clocked out of the ADC. All ADCs have some conversion latency, though this is typically more relevant for delta sigma ADCs because it can take significant time for data to propagate through the digital filter. Additionally, conversion latency is important in a multiplex system because each measurement is taken in series. Therefore, the longer the ADC conversion latency, the longer it takes to cycle through all RTD measurements. For any specific delta sigma ADC, the total conversion latency is often comprised of multiple components. This conversion latency diagram is from the datasheet of the ADS124SO8, a 24-bit 13-channel delta sigma ADC that is commonly used for RTD measurements. These components, as well as additional factors that can affect conversion latency, are discussed on the next slide. This diagram has many important characteristics that contribute to or directly affect the overall conversion latency. One such characteristic is the mode of operation, which changes how often the ADC samples data. For example, the ADS124SO8 has both a continuous conversion mode and a single-shot operating mode. Next, the digital filter order impacts conversion latency, where a higher order filter results in a lower noise but longer latency. The ADS124SO8 Sync 3 filter is shown in the diagram. Within the conversion latency time, there are three distinct zones. The first zone for this ADC is a programmable delay. This delay allows for external analog circuits to settle before the conversion process begins. This feature is useful for multi-RTD systems where the IDAC current is switched from one channel to the next. The second zone within the total conversion latency is the conversion period. Typically, the number of conversion periods is directly related to the filter order. In this case, there are 3 conversion periods because a Sync 3 filter is used. The final conversion latency zone for this device is an ADC overhead time. This is a fixed time required at the end of conversion that cannot be affected by the user. Ultimately, all of these factors combine to generate settled data in a time equaling the delay plus 3 conversion periods plus the ADC overhead. Importantly, this means that the conversion latency for this device using these settings is considerably longer than just the inverse of the data rate. To make this more clear, the next slide steps through an example to demonstrate how this information can be used to calculate the cycle time for a typical multi-RTD measurement system. However, to delve more deeply into each of these factors and the topic of conversion latency, review the application note at the link on this slide. The ADC parameters for this example are given on the left. We will use the ADS-124SO8 operating at 1 kilosamples per second with the Sync3 filter and a delay of 14 modulator clock cycles. Next, let's include the 2-channel, 2-wire RTD measurement circuit that was previously introduced. This specific image shows the bias path for RTD1 in red and the measurement path in blue. In this case, the IDAC is output on bias 0 and the ADC measures between AN0 and AN1. When we start a conversion, the latency for measuring RTD1 is segmented as shown. First, the programmable delay time is denoted by the section in orange. Second, the modulator sampling is shown in green. Since we are using the Sync3 filter, it takes 3 modulator sampling periods to generate an output. Third, the ADC overhead time is highlighted in red. Finally, the total time to measure the voltage across RTD1 is given as 3.211 milliseconds. Note that this is longer than the inverse of the 1 kilosample per second data rate, or 1 millisecond. Let's now measure RTD2. Shown on the right is the bias path for RTD2 in red and the measurement path in blue. In this case, the IDAC is output on bias 1 and the ADC measures between AN2 and AN3. When we start the second conversion, the latency for measuring RTD2 is the same as the latency for RTD1. This is because the data in the ADC digital filter must be completely flushed out before new data can be processed. Ultimately, the total cycle time to measure both RTDs is 6.422 milliseconds. Note that this time does not include any ADC communication time required to change the IDAC or multiplexer settings, though this is typically on the order of a few microseconds. Also, it is important to remember that the conversion latency and resulting cycle time in this example are specific to this ADC. Not all of the conversion latency components shown here exist in every Delta Sigma ADC. Refer to the ADC datasheet for more information about the specific conversion latency for that device. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. True or false? Some ADCs used to measure RTD signals can require multiple conversion cycles for the signal to settle to an accurate value. This settling time is referred to as conversion latency. The correct answer is A, true. Question 2. True or false? When switching multiplexer inputs, some additional delay may be required to account for analog settling. Some ADCs include a programmable delay for this purpose. The correct answer is A, true. That's all for today's video. Thanks for watching.